Hello, my name is Basuki Winoto, and this is my presentation for Big Data Systems course. The topic that I'm going to go over in this video is Datablocks. It's a hybrid OLTP and OLAP on compressed storage using both factorization and compilation. Now let's look why is this a problem. Uh, in database world, it's very common or in application level, it's very common that we have the task uh, to serve mixed workloads, which demands high throughput. By mixed workload, we're looking at OLTP, or usually characterized as write heavy, and OLAP for analytical purpose, which usually characterized as read heavy. Now, the problem here is that we gotta choose. Would it be a system that has a fast write, or would it be a system that could do a fast read? Now, can it be both? A hypothetical use case that I have here to illustrate the problem is that let's think about a system on a retail database, which lots and lot of transaction happens when a customer's purchasing a product, and then it will need to be recorded in the database. And at the same time, you also want to uh, leverage or make use of the data that you've been collected through that transaction. You want to be able to analyze whether you have the correct pricing, and then whether you have enough inventory, or sometimes you need or customer supports need to access that database, and much more, a lot more in the domain of analyticals today. We want to understand. We're trying to dig out information out of the data that we've been collected. Now, I took one of the aside from news website mentioning about how many millions of customers or million of products is being sold in Amazon. To think about it, that would translate into millions of transactions, and that would translate into numerous analytical scenario that we want to be able to cover. So that's kind of put the stage on how important this is. Now, why is it hard? We have to remember that between write optimized and read optimized, there's always a trade-off here. Now, in the transactional, we want a system that could write records, that could write records very fast. So that way, we don't want to do too many data uh, formation or data manipulation before writing. We don't want to do too many uh, fancy processing before writing the raw. Or it would be preferable if we can simply write the raw data into the disk and be done with it. So that would not introduce any additional delay or latency during the write. But then on the other side, on the read side, on the analytical side, the way we read, or the way we take data, it's by query. We want to query the data set, and the query commonly done by selecting on a specific or on a specific uh, columns. Right? So, for example, we want to analyze the number of customers or certain customers with certain criteria, then it would be a column operations as opposed to the original raw data, which was recorded as row basis. Now, a lot of questions there, and I think IBM with the four fees in thinking about data systems, there was always questions around volume, variety, velocity, and veracity of the data. Now, given that problem at hand, The most common solutions is to have two different data systems, with one as a data system that is write optimized, and another one is a data system that is read optimized. And between the two, we have a pipeline which does the replication. It could be a simple copy or a synchronized or a sync operations, or it could be added with data transformation from row-based into a column-based data. So uh, the current solution is more of having each of these tasks, or each of the systems serving a separate tasks altogether. Now, if we look from the 4V's perspective, from the volume perspective, by having that two different data systems, for one for read and one for write, then we certainly have to, from volume wise, it's double the, or we need to double the capacity. We need two separate data uh, volume, right? And then from the data or format perspective, there is a risk of data transformation which change the raw data, which would cause the data change from its original. So there is a risk of warp data there. And then from, because we're doing a replication, there is always risk in the replication process. Today, I believe any replication technology would be considered as failed if it ever introduce any data loss, but it's still a risk. And then from velocity perspective, uh, with the replication, we have the risk of having a delay because of that replication process that needs to be done from the write optimized data set to the read optimized data. Now, the paper proposed a solution that the paper wants to combine these two systems, that is write between write optimized and read optimized, into a single system to make it more efficient, with the expectation also that it would reduce the footprint, as opposed to having two different data systems. You only have one data system. So volume wise would be smaller than two times of the data, of course. But then we have to remember, on any solutions or any systems, we often, more often than not, that we have to deal with footprint, and then read performance, and the third aspect would be write performance. And very often than not, that we cannot choose all of them three, but we have to give some consideration, or we have to compromise which one that we want to pull, or to which lever that we want to pull more in our solutions, right? In more in-depth detail about the hybrid solutions that being proposed in the paper, they call it as Datablocks. So what Datablocks is, it consider it as a container, a self-container, which will own the data with all the metadata that will help us doing the optimal transactional operations, and also the analytical uh, operations, right? The data blocks is in when it, so the way they optimize it by doing two different things, or forming in two different forms. One is the what they call as cold, or is by cold meaning that the data block is in a compressed uh, in a compressed data, and then the other forms is hot data blocks, which is an uncompressed one. So for OLTP, of course, it would be easier and it would be faster when they work on the hot or uncompressed data system, because mainly what they're doing is they want to be able to write in a fast manner. So they don't want to have any additional operations required to write the data sets. So doing so mostly it would be pointing to index in the data blocks and write the data, right? Meanwhile, uh, on the read operation, or the OLAP, it what it does is a lot of operations require scans through the data set. So, and then of course they can afford by having the or operating on the cold or the compressed data. So, and then with compressed data, of course, it would give the benefits of a smaller footprints. So here is how the data blocks layout would look like. There's a tuple count on the first part of it, and then followed with offsets from the SMA offsets, a dictionary, and a data and a string offsets. These are all the offsets of the, or considered as the, I would consider it as the first part of the metadata. And then the second part of the metadata is the positional SMA index. Uh, this is the I would say the important features in the data blocks, that with this positional SMA index, one will be able to uh, decide easily whether the data that they're looking for will be in this data block or not. So as they look into the minimum or the maximum index, and then look into the lookup table, they can decide whether uh, the the data that they will be interested in is we contained within this block. If not, then they can simply move to the next read the next block, right? And then after the positional SMA index, it's followed with the domain size and dictionary, and then the compressed data and string data. So one of the interesting features about the data blocks, or the way data block compress the data, is that it's highly optimized for numerical data, and it's not suitable for, or it doesn't really compress the string. So because the author, they want to make sure that while they compress, or while they save the footprint, they make this footprint smaller, but they also want to make sure that it doesn't hurt the read the read operation. So they choose a very simple or very light, what they call a very lightweight compression scheme. So there are uh, three different scheme, whether it's a truncation, uh, what they don't do compression is on the string data. And then yeah, this is the compression techniques that they use. As I mentioned before, they do a dictionary compression, so one can any chunk can pick, or any portion of the chunk can pick which compression scheme that they want to use. It could be dictionary scheme, and then, or it could be a truncated scheme for compression, and it could also be a single value compression, right? And then this is how the positional SMA helps the scan operations, because the positional SMA, it's pretty much pointed out uh, the index within that block. So whenever we do a scan on a particular index and it's not in that blocks, we can uh, identify that easily through the positional SMA. Now, the scanning process, I think this is okay. From this picture, we can see, and I will only highlight the fact that they're using a lookup table. to point it out to the data as they're doing the probing for the data with the positional SMA. Uh, while this is effective in a scanning process, we also have to remember that having a lookup table, that's another uh, it takes another memory space. Now, with the compression and then with the positional SMA, uh, this is how they put them all together as solutions, or what we call as, or they call as Datablock solutions. Uh, so they utilize, or they take the advantage of vectorized scan, which would be efficient with the help of a SIMD and also AVX2 uh, machine instruction. And okay, so let's if we look at this diagram here, they have, for these two different block, the lower one is the uncompressed chunk, or that would be the hot scan, and then the upper left, that's the compressed data block, that would be the cold data block. So from the cold, we do a vectorized evaluation with interpreted vectorized scan. We do a cold scan, and then it produces a tuple. And then on the uncompressed chunk, we also do a vectorized evaluation with the hot scan, and it will merge or push the matches tuple at a time. And then on the right hand side, it's outside of this scan, it also does just in time compile tuple at a time scan on the uncompressed. Right? So this is the query pipeline within this Datablock solutions. Now, the predicates matching algorithms in the Datablocks is being optimized by applying restriction to the predicates. So there's two level of restrictions, and this helps improving the scan process. Now let's look at the performance measurement. Look at how, so this paper proposed these hybrid solutions for OLTP and OLAP. Now let's see how we met how the performance is being measured, and how the performance would look like, whether these solutions would be suitable for our purpose, right? So if we look at the performance measurement, this is the how SSE or SIMD and also AVX2 set instruction would help with predicates evaluations, right? For a smaller data type bit, certainly these two, the SIMD and then the AVX2, that kind of helps or speed up a lot, gives a lot of improvement and a lot of benefits compared to the regular scalar x86 code. Right? And as we move to the right, as the data types become larger, the widths become larger, then the performance improvement, well, is still there, but it's slightly less than, or it's getting smaller, or less benefit that we can get out of the SMD and AVX2 sets instructions. That said, that it would be we would be a lot more interested in looking at the small data type and kind of process it in a smaller chunk. Now, the impact of restricting predicates, it's very beneficial. It helps the performance or scan performance. Uh, these are the a chart that's showing us how the predicate selectivity would helps improving the performance. This chart gives the cycles per element improvement. If it were, and this is the first predicate selectivity, while the second predicate selectivity is set at the 40% value. Right? And then if we see the compression ratio on the three different scenarios or three different data tests with TPCH, and then the green one is with IMDb data, and the third one with the flights data. These are the three data sets that being used to measure the compression ratio. Now, the compression ratio certainly increasing with the amount of records being the amount of records in one data block. And if we look on the corner right bottom table, we can see that if we compare the compressed with hyper, it certainly gives a lot of benefit compared to the hyper uncompressed. So we can see that hyper, when it's in an uncompressed format, it takes 126 gigabytes on the TPCH compared to hyper on a compressed format. With TPCH, it cuts the footprint up to half of it, to 66 gigabytes. However, we also need to see if we compare the uncompressed regular CSV file compared to uncompressed hyper in the TPCH. Interestingly enough, that with the hyper uncompressed, the memory footprints becomes larger. This has to do with the amount of metadata that we need to add into Hyper-V so that it will be able to operate as we want, or as it's designed in the data blocks. So there is a trade-offs here. Now, if we look at the queries performance in a TPCH on the top left chart, we can see that there are gains, quite a substantial amount of gain by introducing PSMA in the scanning process. And then if we look at the number, look at the bottom right of the table, we can see that the data blocks certainly is faster than regular uncompressed factorized and an uncompressed just-in-time, with the just-in-time uncompressed as the baseline here, right? And if we compare hyper with factor-wise, it certainly have a whole lot of benefits. It's a whole lot faster in general, right? And now let's look at the throughput of the TPCH. The throughput, if we look at the 1, 2, 3, third rows with the data blocks with primary key index and no index. So this is the number here represents the throughput, or the amount of transaction being served per second. So if we compare between, let's compare between uncompressed, or let's compare between uncompressed with no index, with compare that to data blocks with no index. Now we can see a whole lot of improvement there. The benefit is real. So between 36 operations in a second compared to 17,000 operations in a second, that's a whole lot of improvement. With PSMA, the improvement happens even more. On the no index, it improves up to 71,000 operations per second. If we now that's for the no index, but then if we look at, if it utilize the data utilize index, now it becomes problematic, because now data blocks seems to have a lower performance than the regular uncompressed just in time or uncompressed factorized. Right? The other interesting comparison here is the on the data blocks. If it were shuffled uh, on the no index between PSMA and without PSMA for no index, the number of performance or the throughput per second doesn't seem to have any improvement at all. This very contrast to if it were an order. So I would conclude it that the PSMA in data blocks, it's very useful, it's very beneficial if it were on an ordered data set. Now, uh, to kind of conclude this presentation or conclude the paper, the authors concluded that hybrid solution certainly is the way to go. It takes less memory, it has fast query, and it has fast for transactional too. I put this pictorial here as an illustration. Hybrid, it's always makes me think about hybrid car like Prius, which you get the benefit of low MPG and uh, and then you compare that between if you compare it with the gas car, and then if we compare it with the full battery kind of powered car, of course that numbers becomes less significant, right? Now the solutions, if we were to look it in the 4V's perspective, the volume, yes, the memory footprint is smaller compared to having two different OLTP and OLAP systems. It's certainly less than 2 times of the data. And then from the data format, because data blocks only or pick a lightweight type of compression scheme, so it rejects, for one, it rejects bit weaving. Now, whether or not that is a kind of a preferred, is bit weaving preferred, because uh, usually bit weaving would introduce a lot more higher compression ratio, but then as a trade-off of it, then we will have uh, uh, additional delay or additional processing times required, and also CPU power also required there. And then because it utilizes compression, so there is a risk in compress and decompression. The main concern, which is of course changing the formatting from the compressed to uncompressed. If there is any potentially data loss there, it's certainly it's a non-favorable situation. And then from the velocity perspective, the data blocks, as it was shown in the performance measurement, it's best for non-index data set and an ordered data set, because the combination between data blocks and positional SMA, it helps with the improving the scans. Now, for the next steps, the author already mentioned about eager aggregation, that he wants to aggregate sooner, so it will help the scanning process or scanning time. And then early probing on a hash join, it will also reduce the CPU time required to do the scanning. So these are the two possible next steps that the author introduced. And one of the next steps that I can think about is if we can try to balance between hot and cold data ratio, because I believe in these hybrid solutions, if the data set were write heavy, or if it were in the other spectrum read heavy, then it would lose the benefit of the hybrid solution. So it would be, I believe it would be suitable for a mixed workload, but then we need to measure uh, how much or what's the ratio between hot and cold that could take the benefit of Datablocks at a maximum level. So I think that's all my presentation on Datablocks. I hope you enjoy this video. Thank you very much. Bye now.